Okay, guys, let's begin our session. Right now, I muted you. So at last, I unmute all the participants so they can ask their doubts at last. So let's begin the session now. Okay, first of all, let me introduce myself. I am Thrivikram Chakradhar, and right now I'm working as intern and lab mentor in my own Silicon Institute. And meanwhile, in the free time, I am helping LinkedIn community. They are solving doubts, so I'm getting the doubts from them. And in this session, I use it to solve them. I use it to explain them. So let's begin this questions. So the questions I got from the mentor session was. So let's begin and discuss. So these are the questions I got. So one participant asking that, so sir, I want to know what's the VLSI actually. So what are the skills I have to develop? And I'm right now I'm in fourth semester. So what are all the skills and how the skills we have to acquire and what are the tools we have to use? And coming to the participants, so they are asking FSM related doubts. Some are asking clock generations and some are asking overlapping and non-overlapping sequence detectors. And at last, so related to SV concepts, some are asking fork join any, fork join none. So and conversions of one fork to another fork also. And coming to the UVM concepts, so SV UVM sequencer class driver. Why some classes are parameterized and why some other classes are not parameterized? And what is UVM top? So what is the difference between program and class based verification? So whether they are used in our UVM or not, like that. So these are the doubts I am going to discuss in this session. Let's start with the first doubt. Okay, so these are the session overview. So these are all the concepts I am going to discuss in this session. So first of all, I used to discuss about VLSI roadmap and FSM concepts and Verilog and SystemVerilog concepts and at last UVM related concepts. So what is VLSI? So actually VLSI is nothing but there are olden days there are so many transistors related and we have so many electronic related objects. So they are very large in size. So day by day the size is decreasing as well as fast and area also decreasing a lot. So fast is increasing. So how it's actually happened? So it's actually depends on the performance of the chips. So how the chips are made, they are using with the transistors. So whenever the transistor size is less, automatically it is capable of performing more operations. So in VLSI, these are the roles we have. So in the front end role, we have RTL verification, RTL design verification, and DFT roles. And coming to the back end part, we have physical design, STA, timing analysis, and also some analog related roles are also there, and FPGA emulations. So if you see the VLSI flow, so this is the VLSI. So VLSI is actually divided into two, mainly divided into two. First of all, digital and analog. So in digital related also, it's related to front end and back end, it's divided. So these and all the roles, this many roles we have in the VLSI. And coming to the analog, these and all analog layout, analog mixed signal verification, RF frequency, these many roles are there. Whoever interested in these roles, they can explore their concepts while they are getting any related, like they are getting analog related more interested, so they can choose analog roles. If they are interested in digital, they can choose digital and work on these roles and gain knowledge and try to apply the jobs. So these are all the roles we have. Coming to the skills, so what and all the major and minor skills we have to acquire while be a VLSA participant. So let's take in the my major skill, we have to concentrate more on RTL design, and then we have to verify that RTL design, whatever we are getting that RTL design using UVM related that frameworks and SVA. So SVA are not actually assertion related verification and DFT. So these and all we have to work. These and all the major skills we have to require for entering into the VLSI front end roles. And the main thing is timing analysis. So without analyzing any clock, we can't be a good VLSI engineer. So that's why we have to know what and all how to analyze the waveforms, what and all the triggerings and all. Coming to the minor skills, we have to concentrate on scriptings like Python, TCL, Perl, and we have to get some knowledge on Git related concepts. So we are generating that code. While if you want to share with the managers or some other clients, we have to use this Git related thing, and we have to debug. So whoever best in the debug definitely get job in any role. So first of all, we have to debug. We have to get the knowledge on debugging. Coming to at last, every project is will be documented at last. So we have to gain the skill how to document them in a good format using graphics. So these are all the major and minor skills we have to acquire while a VLSI engineer. And coming to the habits for success. So how like so everyone will learn, but someone will be successful. So how they are practicing, how they are achieving. First of all, as a VLS engineer, daily simulation practices. Just take an RTL code or any SV code, just try to execute them and observe the waveforms. Every day we have to practice for analyzing waveforms. Then analyzing log related files. So many files will be generated while running any simulation. So some log files will be generated, FSDB files will be generated. We have to carefully analyze them. Then only we will able to catch the bugs easily. Then we have to follow the coding and timing guidelines. So how while implementing a code, so these structures, these inbuilt classes, these type of inbuilt sentences are some concepts are there. So we have to be particular knowledge about that sentences. So that many that syntaxes and all we have to be very much careful. So we have to follow that coding guidelines. So let's take Python will follow some coding guidelines. Our Verilog and SystemVerilog follow some coding guidelines. So we should be very careful of declarations and implementing the main logic. At last, we have to be stay updated with the industrial trends. Let's take so most industrial trends can be followed through LinkedIn. So especially we have to follow the LinkedIn. We have to scroll every day. So we have to follow. So they are making some knowledgeful like future related concepts will be introduced and AI related will be concept introduced. So following that and all trends definitely helps you for updating and industrial ready. So these and all we have to concentrate. So some are in fourth year. So they are asking that, sir, how we have to start. So let's take up to sixth semester. We are good at learning some basic concepts. So the last semester is the main semester. Let's take. So in the seventh semester, I will suggest to start that first concept related to digital Verilog tool related concepts like QuestaSim. So QuestaSim is very good tool. We can run our Verilog codes, SV codes, and even UVM also will be run in this QuestaSim tool. So concentrate on learning these concepts as well as practice the tools. So in 8th semester, start at least try to do at least one project related to RTL and full UVM related projects. And so finally, parallelly, while working in 8th and semesters, 8th and 8th, 7th and 8th semesters, so work on interview oriented concepts. So explore every apps like have ambitious box and Glassdoor related apps. There we can get previously interview questions. So for product based as well as service based. So just explore them and write them and try to explain to your friend, and in this way we can get confident of explaining and all. So at last, post graduation. So some are interested in post graduation. So they can do post graduation using, they can apply through GATE, and they will be in good institutes like NITs and IITs. They can concentrate on analog and digital concepts. So at that time, at the third and second semester, they get internships. Very good opportunity. So this is the roadmap to follow in the fourth year. Okay, let's start our first related. So some are asking FSM related doubts. So what is an FSM? So actually FSM is a sequential circuit. So it actually contains both logics and it has some memory related concept also. So it can able to store the bits of data. So this is actually nothing but first state, second state, like that. One state, another state, we are going based on that input given. So output depends. So there are actually two types of FSM. Let's explore them also. So FSM can be of it depends on state and it depends on both state and input. Based on these two criteria, FSMs are classified into two types. First one is so this is actually, so FSMs are two types. One thing is first one is Murray related FSM and second one is Mealy related FSM. First, Murray, what is Murray FSM? So Murray actually depends on only current state. Let's take these are the states. So Murray will depend on only first the states only it depends. It actually don't depend on the current input. Whereas coming to the Mealy, it both depends on state as well as the current input. Coming to the output changes synchronous, like coming to Murray, output changes synchronously with state transitions. See, output actually changing. So if you are giving this, let's take this as naught. So this is the first state of Murray. Whenever we are giving input to one, it changes to the actually it's moving to the second state. So these two FSM are actually detecting 101 sequence and it is non-overlapping type. So these two actually these two FSMs we have. let's take let's explore Moore related FSM. So Moore related FSM output depends on only on the current state. See, S0 is changing to S1 whenever we are giving input 1, and it's going to the S2 whenever we are giving input 0. And same 101 is detected. It at last went to the last state, and the output is 1. So we got the at last 101 sequence is detected. We are getting the output as 1. Similarly, so if you like similarly melee also, one we are giving 1, it going to the second state, and if you are giving 0, it going to the third state, and if you are giving again 1, it going reverting to the first state. So compared to melee and Moore, so which is best, someone will get the doubt. So it actually depends on the application of the question. So some are very efficient on Moore machines, some are efficient on melee machines. So here states are less, like in the Moore machine we have one state extra. Coming to the melee machine, we have right number of states. So this because of more number of states, area of the chip also will be increases. So coming to the melee, area of chip will be decreased, but melee will be less used because it prone to glitches. Some glitches will come. That's why melee is less preferred when compared to the Moore. So we will go explore next concept. So some are asking, sir, how we have to generate 50 megahertz clock. So actually, this is the syntax, main syntax we have to follow for generating a clock. But how we have to generate 50 megahertz clock? First explore. First we have to convert this 50 megahertz clock to the time period. So here the input frequency is asking 50 megahertz. So how we have to do? So what actually 50 megahertz? So 50 megahertz is nothing but in 1 second 50 into 10 to the power of 6 clock pulses are generated. So like this many clock pulses are generated in 1 second. That is nothing but 50 megahertz. So how we have to calculate the time period for that megahertz given frequency. So you know that time period is nothing but 1 by frequency. So 1 by 50 into 10 to the power of 6 hertz. So this actually if you calculate 1 by 5, you know the value of 0.2, and I moved this 0 to here. It will, if you go denominator when moves to numerator, we will get 10 to the power of minus 7. So at last we will get 20 nanosecond. So with the given frequency of 50 megahertz, we got the time period as 20 nanosecond. So with this 20 nanosecond, we can generate a clock. I will show the Verilog code now. We will explore the Verilog code also. See. So hope my screen is visible to all. So this is the Verilog code of how to generate a 50 megahertz clock. So first of all, we are generating what we are generating. So we are generating 50 megahertz code, 50 megahertz clock, and it belongs to the like we got the 20 nanosecond time period. So let's see. So here actually nanosecond. I am declaring the tick time scale as nanosecond. Why I am declaring nanosecond? So that clock should come in nanosecond, and the display also clock should be nanosecond. So I declared 1 nanosecond. This is unit. This is time unit, and this is time precision. So we will call it as time unit and time precision. This is how we have to declare the tick time scale. So in this, according to that, the clock will be generated, and for that values that values will be multiplied. Then we will go to main code of this is actually behavioral code of Verilog, how to generate the clock. So I declared a signal like clock. So within the initial begin block, I am initializing the clock to 0. In forever loop, I am generating. This is the main syntax of how to generate a clock. So here the clock will toggle for every 10 delay. So where every 10 delay, the clock is going to toggling. So in another initial block, I'm monitoring, I'm right monitoring. So what the value of clock for every 10 nanosecond it will display. I'm writing a monitor, and this is actually in EDA playground. If you want to see the waveform, we have to use this particular syntax. Then only waveform will be generated. So this is actually the code for generating the 50 megahertz clock. So let's explore the output also. So let me run this code first. See, the clock is so that the clock is toggling for every 0 for like let's take in 0 simulation, clock is 0, at 10 clock becomes 1, at 20 nanosecond clock becomes 0. So this is how we will observe the waveforms. So let's explore that. So time, let me refresh this, clock will come. So I selected that compiler, online compilers, all like River Pro. This is actually a free compiler, and we have to enable this to see the waveforms. Yeah, the waveform is generated. See, so this is the waveform of 50 megahertz. Let's see the time period. Here, the time period is in nanosecond only. See, from here to here, how much time period is actually? Time period is nothing but one. Like this is a clock off. This is clock on. So what is this time period from here to here? 20 nanosecond. So this is how, if the clock period has 20 nanosecond time period, so automatically the full frequency in 1 second we will generate 50 megahertz of a clock. So this is how we have to generate any type of clock with the given frequency. Okay, let's go to the next question. So one guy is asking, sir, I want to detect both sequences, 1011 and 1100 overlapping FSM. So first we will explore. So first we have to know that state diagram. Then we will explore the Verilog code. So this is the state diagram provided. So let's take. So here S not state. Let's take. First we will detect double one 1011. First we will detect, and after that we will detect 11100. So I am writing for 1011. So here S not state I declared whenever I reset. So whenever I give input, so 0, it will stay in the same state. Whenever I give the input as 1, it goes to the next state. So since it detected first, I am detecting both from MSB. So I have given 1 as input. So it going to the next state, and the output is 0. Why? Because the complete sequence is not detected. That's why output stays as 0 only. So whenever I give a second input, so as 0, so it goes to the second state. So this state can see, if you see the state, it is detecting of 1 0. Whenever we are giving 1 0, it goes to this state. So it is able to detect 1 0. So again I am giving as 1, so it goes to the next state, and it is detecting 101 sequence. And if at last I have given 1, the last input, so output will changes to 1 since it detected 1011 sequence. So this is the state of detecting 1011. Similarly, after writing this number of states, we have to detect this also, right? So we will go explore this also. So S1 is the state which detected one bit that one is given. So we are we have to detect the remaining these three bits also. So we are going to the next state. Whenever one bit state is detected, whenever we given another one bit, so another one, it goes to the S5 state because it's detecting two ones. So we are able to write a state which is detecting of two ones. So again, if you give 0, it is able to detect 110 sequence. So similarly, if you give another 0, it will detect 1100 sequence. So these two tracks are completed. Now for every state, so we have to able to see that whenever we 0 is given, it is going to S2. So what if we give 1? So we have to see, right? For every state, we have to verify two inputs. Whenever we given two inputs, it will go to the second state or next state. So let's take here we are in S1. So whenever 0 is given, it's going to the next state. Let's take S2. 10 is detected. Whenever we given 1, it's going to the S5 since double 1 is detected. So in this way, let's go to the S2 state. So here, whenever 1 is given as input, it's detecting 101. What if we give it 0? So automatically it goes to the S naught state. Like this, for every state, we have to write the next states as, like, whenever it detects 1, to which state it will go. Whenever we will give an input as 0, which state it will go. We have to detect that one. So in this way, we have to draw the FSM for detecting both 1011 sequence as well as 11100 sequence. So this is a overlapping type. Whenever, let's take when these two sequence will be overlap. So if after giving 1011, if we give again double zero, so it is able to detect both sequence. So that is nothing but overlapping sequence. So let's explore the Verilog code also for this. So first of all, this the diagram is very important. After getting better analyzation of diagram, we have to give random sequence and we have to verify the design. This is the Verilog code. We can explore the Verilog code also. So this is the RTL code and this is the test bench code. In RTL code, first I am declaring the module. So module name I am declaring as 2 sequence detector. In this FSM, I am taking input as sequence in. So main thing is, since it is sequential circuit, we have to use clock as a means. So depending on clock only, we are changing from one transition to another transition. We are giving inputs. So this is another signal I am using reset. Why I am using reset? So if at any time when I reset, that FSM should come to the initial state. That's why I'm using reset. And detector out, it is nothing but our output. So I am declaring both inputs and outputs like this. So input clock, input reset, input sequencing, and output as register. So then I have to declare our states, right? So here, if you see S0, S1, S2, S3, S4, these are all the states. So I have to declare the states also, right? That's why I am declaring here. So as parameters, S0 as 3 tick 0, 0, 0. So in this way, we will declare all the states. Then we have to declare register. So why I am declaring 3 down to 2 down to 0? So it is capable of taking 8 states. So here, how many states we have? If you observe the diagram, how many states, total states we have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 states are there. We can declare 2 down to 0 means automatically it is able to take 8 values, right? So that's why, so I declared 2 down to 0, current state and the next state. So current state and the next state, and I am writing. So in any FSM, we have 2 always block. One always block which is of sequential type, and another always block of combinational type. So this is actually sequential always block. Here we are declaring. So I am actually triggering that states. So let's take depending on the clock only, I am changing from one state to another state. That's why I am writing always at the passage of the clock and passage of the reset. So at every reset, so if I, let's say I'm giving begin end. So since there are multiple statements are there, I'm using begin end. So whenever I use the reset signal, whenever I make the reset signal as high, current state should come to the S naught. If reset is not high, current state should be assigned to the next state. So this is the sequential logic we have to write like this. Coming to the combinational logic, so we have to write like always at current state and sequencing. So in this, these are the sensitivity list. In this sensitivity list, we have to pass our current state and sequencing. So I am writing begin end. So there are multiple statements are there. So I am writing a case statement. So in case I am using current state. So this is our current state. Current states are nothing but our S0, S1. That states are nothing but our current states. So let's take, if I am in S0, so whenever the sequence input is 1, the next state should go to S1, or else the next state should go to S0. If you observe the diagram, whenever I given the input as 1, it should go to S1, or whenever given I input as 0, it should stay in the S0 state. So that this logic, this diagram I am implementing in the logic manner. Let's take this fam in S0. If input sequence is 1, I should go like next state should be S1, else next state should be S0. Like that, depending on this diagram, I am writing the code for every state. Like this we have to write, and at last we have to write the logic for output also, right? Since it is a Moore FSM, every state has its own output. So the S4 is a state of detecting 1011. Here automatically the output will be 1, and S7 is the state detecting 1110, and the output is 1. Remaining all the states are 0. Like that, if we declare like this, where for every output logic we have, for every state we have unique output. So for S0 we have output as 0, and every state we have output as 0 only. For only S4 and S7 we have output as 1, and we have to write, we should not forget about default in every case. So if we are using any case statement, we have to declare default also. So here I am declaring default as S0. For output logic I am declaring default as 0. So in this way we have to write FSM code for Moore machine. And coming to the test bench, we have to give the inputs, right? So what are the main inputs in the FSM? So here declaring the tech time scale as 1 nanosecond per 1 picosecond. It is mandatory or not? It depends. So sometimes some applications, some guys will ask, we also need that frequency related concepts. Then we have to declare tick time scale. And we am writing a module. So in this module, I am going to instantiate this design and I am trying to give the inputs. So all the inputs here, which I declared in the module, can be taken as reg in the test bench, and output can be taken as wire. So here I am instantiating my design. What is my design name actually? See, two sequence detector. I have to write two sequence detector and I have to give an instance name. So instance name very much mandatory. So this is the module name and this is the instance name. So here I am instantiating. So what is this difference? Dot sequence in what? This is actually the main, whatever the design I used, the name, that is nothing but that name should be here, and I'm passing some another sequence in, that is actually this one. So this and all. So actually there are two type of instantiation. So order based and the name based. So it is actually name based instantiation. So I am after that I am generating what clock I am generating. So I am using always block. Actually it's actually triggering, like it's actually going from 0 to 1 transition whenever it faces the delay. So for every 5 delay the clock is toggling. So it's after 5, let's take the initial value of clock as 0. After 5 it's toggling. So clock automatically generated from 0 to 1 like that after for every 5 nanosecond. So I am using initial begin. Why am so I am dumping this file. This is actually mandatory. While if you are using EDA playground, these two lines are very mandatory, because so the waveform is generated, but it should dump in another file, right? That file only we are reading. So these two main lines are very mandatory. I am initializing the clock here, and I am making the reset as 1. So since we used here active high reset, the current state will go to S naught. So the sequence, okay, let me given at 0 nanosecond, I am giving the input as 0. And after 10 delay, I am making reset as 0. So, so whenever I am reset is high, it's in S naught state. Whenever reset is 0, it goes to the else part. At here, our main logic and transition of states will start. Whenever our reset is 0, our main transition of states will start, depends upon the input. I'm taking as inputs 1 0 double 1 and one sequence I am detecting. So since it is overlapping, I am in parallel I am using double 1 double 0 also. So both sequences are detected since it's overlapping. After some delay, after 20 delay, I am finishing. So I am terminating my simulation. At last, this is and all for observation purpose. In our console, if you use this display messages, so it will display the output in our console. Okay, let me display the waveform for better analyzation. So I am selecting the tool as Aldec River Pro because it is a very free tool. Remaining all they are actually commercial tools. If you have any college related email, you can access these tools also. And I'm using and I'm owning this EPWay. Like EPWay, if you on this one, that only makes our waveform to be visible. So let me run this code. See, the waveform is generated. So as I said before, our FSM like RTL code is triggering at pause edge. So let's take the main inputs we have to observe. Here the clock is generating and my current state is 0. So this is S naught state, 0, 1. These are all what? They are all actually S naught, S1, S2, S3, S4, S5, S6, S7. These are all states. So my current state is 0. And let's take here my reset actually. After 10, I made the reset as low. Now my main operation will start here. So let's take so whenever I am in S naught state, whenever I give the input sequence input as 0, it will stay in the S naught state only. See, this is the current state and this is the next state. So in what is the current state? Current state is 0 and I am giving input as 0. Where it will be? So let's take this is the current state. I am giving the input as 0. It will stay in the same state, right? So we have to observe here. In positive, you have to observe this one. So I am in 0 state. I am giving input as 1, 0. So it will be in 0 state only. Let's take this one. Let's take example. So let's take this example. Based on this example only, the waveforms are generated. So let's take I am in S0 state. I given input as 0. It goes to the S2 state. As I am in S0 state, I am giving input as 0. It goes to the S2 state. See, here I am in S1 state. So let's take I am in S1 state. I am giving input as what? Before input we have to check this input. I'm giving 1, and my current like next state will be goes to the S2 state. Like this, whenever we are giving based on this current state, uh, we have to mainly observe these three. So this is the current state, and this is the input, and this is the next state. Next state will come at the main positive edge only, because we write the logic as it should be triggered for every passage of the clock. That's why I'm getting a next state also at passage only. Like this we have to explore the we have to analyze the waveforms. So mostly it came correctly only, so it's running properly. So I verified before it's correctly running. In this way we have to run this waveform, and we have to write the Verilog code like this. Similarly similarly non-overlapping also. First of all, we have to draw the transition diagram. Based on this transition diagram we have to code like this. So in this way we have to code. We can just a mostly this state next state logic we have to change. First of all, make sure that your state diagram should be correct, and at last we have to code perfectly using proper syntax. So coming to the next doubt, someone are asking, sir, what is the difference, why we are using fork joins and all. And so we have threads and all. Like let's take initial beginning, we have always we have. So why we are using forks? So actually is this fork join none, and fork join any will make us so there are threads inside every block. So what we want to make the thread run concurrently. So every thread should start at same time. So we should use fork join any, fork join none. So these three concepts have different uniqueness. First of all, let's take fork join. Fork join actually parent waits for all child threads. Let's actually I taken the code also for analyzation. Okay, these are all the three forks we have: fork join any, fork join none. So let's explain fork join. So in fork join we have, let's take three threads are there. So three threads are nothing but it's actually lines of code. Let's take dollar display statements also comes under threads. So in fork join I have three threads, three display statement. So three display statements. First display statement is working after 10 delay. First display statement is executing, and after 20 delay, second display statement is executing, and after 30 delay, some third display statement is executing. So when that thread will come out of the loop, so whenever use for you if you use fork join, that will come out of the loop at that thread which executes at maximum time. So whenever let's take after 30 delay we have another thread. After completing the 30 delay, fork join will exit, and it will continue executing the parent threads. So if you use fork join any, it will see what thread has a minimum delay, and it will see the minimum delay, and it execute that minimum delay thread, and it comes out of the loop. But if you use fork join none, so it will start every thread, but it won't wait for any delay in the thread. So it will come, it will just start the threads, and it will come out of the loop. So it will actually every thread will run at backside. So some are asking how to convert one thread to another thread. We will explore that Verilog code. So if you want to convert fork join any to fork join, if you want to convert fork join any to fork join none, so what mechanism we have to implement? For that I just collected some snippets. These are all the snippet. So let's explore the first snippet. The first snippet is See, in module I declared. In the main module, I am writing my logic. So in initial begin block, in the runtime, within the begin end, I am using fork join any. So I am converting here what I am converting fork join any to fork join. So fork join any behaves whenever it has less delay, it will come out of the loop. But whereas fork join behaves after executing the more delay thread, it will come out of the loop. So let's see if we use fork join here, when the thread, which thread will execute, which after completing of this 30 delay thread, it will come out of the loop if we use fork join. So, but I am using here fork join any. So if you use fork join any, it after executing this thread, after executing the less delay thread, it should come out of the loop. So, but it's behave like fork join. If I am using fork join any, but it behaves like fork join. Why? So I am using here wait fork. So it will wait. It will wait for every fork join thread. This after completing of every thread execution, it will come out of fork join any. If we use wait fork, in this way, using this syntax, we will develop fork join any to fork join none. Fork join. So let me execute this thread. See, it is actually fork join. I used a fork join any. Fork join any if I use means it should come after this display should come after 10 delay. But if you see, thread 4 is executing at 30 delay. So this thread is behaving as what? Fork join, fork join. So if I am using fork join any, but it's behaving like fork join. In this way we can convert fork join any to fork join. Coming to the next concept, let me comment this out. So next concept is converting fork join any to fork join none. So fork join none means what? It should come out of the loop at zero simulation time. Just it start every thread and it come out of the loop and it execute the parent thread. So see, here the parent thread is this one, and these and all the child threads. So here I am using 20 for the first and 10 for the thread 2 and 30 for the thread 3, and I am using fork join any. So but it will behave like fork join none. See why, how we can say fork join none, it behaves. So if these three threads are not started, so they will run at background, but this thread should come at zero simulation time. Then we can say that fork join, it will behave like fork join none. So let's explore the output also for this. See that thread 4 is executing at zero simulation time. So this behavior is like what? Fork join none, right? So in this, by using fork join any, we can developing fork join none. So we have to use fork wait fork inside fork join any. Then it will behave like fork join none. But if we use after fork join any wait fork, it will behave like fork join. So this is the small difference we have to keep in our mind. We'll explore some other two snippets where the fork join none is behaving as fork join. How? Let's explore this one. Fork join. So fork join none means what? So all the child threads will run concurrently, and within zero simulation time, that fork join, like that loop should come after that, and whatever the parent thread, that should be displayed. That is actually the concept of fork join none. But it will behaving as fork join. Fork join means what? After whatever which thread has the maximum delay, after completing that thread, it should exit. So that's the behavior of fork join. So how we have converting this fork join none to fork join? We are using wait fork after fork join none. So I am using fork join none, but it is behave like fork join. Let me run this snippet also. So without 0 errors, it compiled. See, after when this fourth thread 4 is executing at 30 delay, so I am using fork join none, but it is actually behaving like fork join. So this is how we have to implement the logic of fork join none to fork join. Similarly, fork join none to fork join any also. Let's explore that code also. These are all actually interview based questions for checking our knowledge on weight forks, that like that. This is what fork join none to fork join any. So fork join none is behaving like fork join any. So we are using wait events for better getting that output clearly and getting the required output. We are using events and we are triggering the events and we are waiting for the event. So whenever let's take this 20 thread is completed after 20 delay and it will be triggered. So after triggering of this, this wait statement will be executed. So here we have three delays, 20, 10, 30. Which delay will be executed in less number of time? So this thread will execute at less number of time, and after that this will be triggered. After triggering of this event, this is actually waiting for this triggering. Whenever this event is triggered, it will wait. Actually, it's waiting. After this event is triggered, this statement will be displayed. Like this, we will convert our fork join none to fork join any. So let me simulate this code also. See, fork join none to fork join any means what? So our output thread 4 is coming at 10 delay only. So it's behaving like fork join any. Fork join any behaves when how we can say fork join any. So whenever this thread has a less delay, like we have three threads. So which has a less delay here? 10. After completing of 10, it will come out of this fork join none. Then this display is happening. So in this way, we can say that the fork join none is behaving as fork join any. So in this way, we have to convert one thread to the another thread. So I explored. In the next session, I will explain how to convert fork join to fork join none and any also. Right now, this is the main thing we have to work on. And these are the thread related concept we explored. And coming to the next doubt. So one of my student is asking, so why sequencer and driver, which are we are using in UVM, right? Why they are parameterized? So some actually we have so many classes in UVM. Let's take test class is there, UVM test is there, UVM environment is there, UVM like agent is there. So we have drivers, monitors, sequencers. So in that among only some classes are parameterized. Why so only some classes are parameterized? Let's take. So what is the benefit? First of all, we have to explore what is the benefits of parameterization. See here, my driver is extending from UVM driver. We know that UVM driver is a parameterized class with a transaction class. So we declare a transaction class. So we are like this driver is used to drive and is used to know that so I am driving this related data. Let's take I am driving int data type data. Like we have so many classes. They can be parameterized with int data type. They can be parameterized with class data type, another class data type. Like this, we are actually parameterizing every class. So what is the benefits of parameterization? So type safety and reusability. For increasing the reusability of the code, we are actually parameterizing the class. Why particularly sequence and driver? See, in driver, what we are actually doing. So we are driving the transactions to the DUT. So so driver should know that what it's actually driving. So that should be parameterized. So whenever it is parameterized, it is able to know that yeah, that I am driving this type of data and this type and I'm sampling this type of data. So here driver actually driving packet related data. So packet is nothing but our transaction related data. It's driving. So type safety and reusability purpose, we are parameterizing, and sequence and driver are parameters, so they can work for any type of sequence item and transaction, allowing ease reuse and some structures of different data without rewriting the code. That's why we are first of all we are parameterizing. Why actually sequence and driver? So you should know. So this class is able to be built to drive this type of data. Let's take sequential type of data, like transaction type of data. It's able to drive. So that's why we are parametering. Yeah, I'm saying that. So driver should drive this type of transaction. So and again, sequencer should get the transaction from the sequence and should drive to the driver like that. For that purpose, we are parameterizing those two classes. So if we want to drive int data type related data, we can parameterize that also. So we can parameterize with int and we can able to drive only int data type data. But here we are parameterizing with sequential type. So sequence item type. Then only sequence item related data will be driven to the DUT through the driver. That's why we are using this concept of parameterization and all. So the next doubt is, so what is actually UVM top? Whether it is component class or object class. First of all, I want to say that actually UVM type is not is actually handle. It's not component or object. First of all, it is an actually inbuilt handle of UVM root. So where it actually UVM root will exist? So we know that the hierarchy of the UVM. So where the UVM starts, it will start from UVM void, and from that UVM void, UVM object type of classes will be extended, and after that from UVM object, UVM component type of classes will be extended. From that UVM component, UVM root is extended. So what is actually this UVM top is the inbuilt handle of UVM root. So it can able, so in this UVM root have so many methods. So every hierarchy, every component below this UVM component and UVM root can be controlled using UVM root. So every that methods and all will be present in UVM root. So UVM top is a handle of UVM root. So why this actual, what actually UVM root will do? So you can manage simulation phases, hierarchy, and printing. So we are using UVM top. So how we are like we are working, while we are working on UVM related thing, we are printing the topology. How we are printing the topology? So UVM underscore top dot print underscore topology we are using. So UVM underscore top is the handle of UVM root. Print underscore topology is a method inside the UVM root. So we are just calling that method. Actually, that method is implemented in such a way that it is able to grab, it is able to know that what and all the components are created perfectly. Then it should show the output in our console. Like that, UVM top UVM root concept will be introduced. So it actually provides global access to the UVM tree. What is UVM tree? You know that UVM tree structure, right? So from void, components classes, object classes are extended from component classes. Some drivers, monitors, everything is extended from that component classes. So this is every UVM tree can be like global axis, like UVM root and UVM top has a global axis of the UVM tree. Any component can access this. UVM top can access any component, any methodology, any method can be accessed through this inbuilt handle. And coming to the UVM root, so UVM root is a base class of very top of the UVM component. It's derived from the UVM component and acts as singleton parent of all UVM components. As I said before, it's actually an inbuilt handle of the UVM root. So someone asking, sir, why we are using program blocks? We are not using program blocks in UVM, and we are using class-based verification in the UVM. So let's explore why we are using programs in SV, not in the UVM. So what is actually program block? It's actually a test stimulation and simulation behavior. We can generate a stimulus from that stimulus, and then deterministic execution order. And we cannot control the simulation phases also. Let's take in UVM, there are so many phases. Let's take connect phase, build phase. These phases all we have. We can't control that phases using program blocks. And coming to the OOPS related concept is introduced, right? So it's limited OOPS. So there are so many concepts in OOPS. So program blocks can be limited for that concepts. So reusability is less and modularity is less in program blocks. Coming to the class related blocks, so class related concept, there are so many advantages of classes when compared with the program blocks. So here class based verification comes with a modular, it will be reusable, scalable test benches will be developed using class based verification. So we can control via UVM phases. So everything it's in our control is a class based declaration of classes. And suppose let's take parameterized inheritance, like as I said before, we have the concept of OOPS. So it will support OOPS related concepts, inheritance, polymorphism, So there are so many advantages of class when compared with the program blocks. That's why we are just using class based thing only in UVM. And it can able to handle virtual methods, transaction objects, and messages also. So classes have virtual methods also, it can able to tackle, and we can manipulate our own thing. So especially why program blocks are not used in UVM. So no hierarchy is there, cannot be extended easily. So program blocks have don't hierarchy, so they don't extend easily, can't support multiple configurations. We have configuration facility in class, but we don't have a configuration facility in the program blocks. So and class based design ensures flexibility and scalability. So based on these three, there are so many advantages for the class, right? That's why we are using only classes in UVM, not we are not using program blocks. So this is the main clarity we have to get. So some are asking, sir, there are virtual classes in UVM and non-virtual classes. So what are they? Let's take why virtual is introduced. In like virtual and non-virtual. Non-virtual can be called also concrete classes. In concrete classes, what and all we have? UVM driver, UVM sequencer are related to the concrete classes. Already some body is declared. We are extending that and we are adding our own body to that. And coming to the core functionality, the main functionality of driver was what? It drives the DUT, like it will drive the stimulus to the DUT pins. And sequencer provides the transaction, and the sequencer getting transactions from the sequence. And it's a ready to use foundation component. So always classes are ready to use. Coming to the virtual classes, so we have UVM sequence, monitor, and agent. They are actually virtual classes. So based actually their template is customizable. Like we have different related duties. So we can customize our own sequence classes, monitor classes, and agents based on the protocol. So that config like most customizability will be there in virtual classes. And basically they have support polymorphism must be extended. So this can be extended or not, it's no problem. But these classes should be extended. Then only we can create the object for that classes. So let's take an example. Let's take driver and sequencer can be taken as engine of the car. So driver and sequence can be act as engine, core components with fixed functionality. So coming to the monitors and sequences, attachments, customizable like project protocols. So what actually here I am explaining means, so here we have in every car we have an engine. So that engine can't be changed, but we can like let's take one car, that engine is fixed. So we can change, we can customize our car with own colors, right? That colors and all our virtual base classes. This engine is nothing but our concrete class. This is fixed. So for our like remaining components, we have to extend them and we have to create the object. This is the main difference between our concrete classes and the virtual classes. So at last it's completed. Our session is coming to end. So before ending the session, I want to give the drive axis. So I want to introduce what and all the drive will contain. So actually, when I started the course, I used to collected so many information from the LinkedIn. So they actually LinkedIn from I collected so many PDFs related things, and some I actually buy it from others. So they are actually contains. So actually these and everything will be used for interview preparation and job cracking. We can explore everything. So here I collected for digital related concepts. So many books I collected, as well as some important PDFs related for problem solving. So this full drive will be can be accessed for everyone, so they can explore and they can learn. Let me explore for digital. So these are all the digital related concepts I collected. So Verilog, system Verilog. So many are asking. So assertions and constraints I created for them, and problems. So SP related problems. What are the practice problems for inbuilt getting more knowledge on this. And we have protocols and all, right? At last we have should be aware of protocols. So protocol nodes related thing, everything I collected. So I'm giving access for who are need them. So many members got the access and they are learning every day. And interview, this is the main thing I want to say. Interview I collected, interview preparation for every company I collected so many questions from different sources, and also extra related interview questions. So let's take recently I collected BitSilica. So from BitSilica, these are the interview questions they given. Like this interview oriented also I am helping students by giving access for this drive. So actually, if anyone interested, please message me. I will access this drive, and that's it.